So in section 8.1, we learned about confidence intervals. We learned how to interpret them. We learned about confidence levels, and we learned how to interpret those. Now I'm excited because you guys are going to learn how to create the intervals that you know how to interpret. Okay? So we're going to focus on proportions. 8.2 is all about proportions, so we're going to focus on that. So before we learn how to actually construct the interval, we need to remember some things. Are you guys ready? Are your memories warmed up? Here we go. Ocean, are you ready? All right. Okay. No, everybody's memories are warmed up. Here we go. What point estimator do we use to estimate the population proportion? What estimates P? P hat estimates P. Perfect. P hat estimates P, you guys. Now, we're going to go back to our chapter 7 days. What was the mean of the sampling distribution of the sample proportion? I just asked you guys, what is the mean of P hat? There was a, quote, formula for this. What is the mean of P hat? It was just P. The mean of P hat was literally just P. Okay? Now, this one was an actual formula. What was the standard deviation of the sampling distribution of the sample proportion? What was the standard deviation of P hat equal to? Anyone remember?
Bottom of the page.
Shh, Jenna. It was the square root of P times 1 minus P divided by N. Awesome. Now, do you guys remember what condition did you have to check anytime I asked you for this standard deviation? And it was not the large count condition. Good. We had to check the 10% condition. And remember, the 10% condition was that 10 times the sample size of little n had to be less than the population size of big N. And I've been telling you guys for like a month now that I would tell you why this is important, and today is that day. Just not yet. Give me a few minutes and I'll tell you. So today is the day that we're going to talk about why that 10% condition is a thing. All right? Now then, how do we ensure that the sampling distribution of the sample proportion is approximately normal? What did we do to check to make sure that a proportion distribution was normal? Central limit theorem was for means, but you're on the right track there. The large count condition. We had to check the large count condition. As long as the large count condition was met, we had an approximately normal distribution full of P hats. Anybody remember what the large count condition was? Like, how do you check that thing? N times P had to be greater than or equal to 10. The 30 was the central limit theorem. That's going to come back when we start talking about means. So that'll be next week. All right, N times P has to be greater than or equal to 10. What else had to be true, you guys? N times 1 minus P had to be greater than or equal to 10. If both of those things were true, we could say that our distribution that was full of P hats was approximately normal. All right, you guys. Now, I have interesting news for you. We no longer have the population parameter. Remember, I told you guys you're no longer going to know the true population value. It's not going to be given to you in the problem anymore. Just like you don't know how many blocks are in this bucket. So what are we going to do? How are we supposed to use all these formulas that have a bunch of p's in them when I don't even know p? We're going to replace it with the sample proportion of p hat. So here's the deal. If you don't know the truth, put a hat on it. All right? If you don't know the truth, the true p, put a hat on it. Make it p hat. So that means that the mean of p hat, we're going to estimate that p with a single sample that we take. Because we're such good statisticians that our samples are going to be on point. So we're also going to take our standard deviation formula and we're going to put hats on the p's. Now notice that we do have a slightly different notation for this. It is S sub p hat. That is the standard deviation of a sample for p hat. All the p's get hats on them. But you guys, it's the same formula. So basically, when you do a problem, if you're given the population value, which is rare now, going forward, use it. But if you're not given the population value, use your sample value. That's all. No big deal. So if you have the actual population value, then you can call that the standard deviation. But if you are using p hats, it's called the standard error. Kind of like the margin of error. We got a standard error. It's because we're using estimations for the truth. Okay? All right, this little section that you guys see here is on your actual AP Stats formula chart. So again, you don't have to memorize this. So we have a bunch of P's. We're just going to put hats on them. It's going to be great. Cool? Mm-hmm. Cool. All right. We're almost there. So what we're going to do is we're going to take the general format of a confidence interval, and I'm going to turn it into an actual formula, okay? So here's the general format. We've got our... So we've got our point estimate. The point estimate, you guys, where is the point estimate located in the interval? Right in the middle. Boom. Smack dab in the middle, right? So we take that point estimate and we add and subtract the margin of error. Now, we are specifically talking about proportions in this little section that we're talking about here. So here's the deal. Our point estimate for a proportion problem is p hat. That is what we're going to use to estimate p. That p hat is going to be the middle of our interval. Then we're going to add and subtract the margin of error. So here we go, guys. I'm going to break down the margin of error for you. The margin of error is actually comprised of two pieces. Okay? So here's what the margin of error is made up of. A critical value and the standard error. The margin of error is made up by multiplying the critical value times the standard error. Now, we've kind of seen that the margin of error is a measure of variability in our interval. It tells us how wide our interval is going to be. And there were two things that made our interval change how wide it was. We talked about if we increase our sample size, if we increase our confidence level, our margin of error got bigger and our interval got wider, okay? That happened because of the critical value. The critical value comes from your level of confidence, okay? So your critical value comes from the confidence level. The notation for the critical value for a proportion problem is Z star. It's Z with a little star up where you would normally see an exponent. Z star. That is your Z star critical value for proportions. Does anyone remember what a Z score is?
Oh, it was varied from a standard deviation?
Absolutely right, Catherine. This Z star is exactly a Z score, okay? So this is a Z score that tells how far from P hat we need to go to capture the true P. That's a comma. Based on how confident we are. The Z star critical value is going to be the Z score that tells how far from P hat we need to go in order to capture the true P, and that's going to be based on how confident we want to be. Do we want to be 95% confident? Do we want to be 99% confident? It tells us how far we got to go, okay? We're going to talk more about Z star critical values first thing tomorrow. I'm going to actually show you guys how to calculate them, how to get them for any percent confident that you want to be. And the good news is they never change. So once you know what it is, you just know what it is. But I'm going to show you guys how to calculate, and we're going to do more with Z star critical values first thing tomorrow, okay? Standard error. We already talked about this. It is just the P hat, 1 minus P hat divided by N. We use P hat to estimate P, so we just replace the P hat, or the P's with P hats in the formula. And that's the standard error. So, remember when we talked about increasing the sample size? When we increase our sample size, we decrease our interval. And here's why. When I increase my N, it makes this part of the equation smaller. When this number gets bigger, this gets smaller. And therefore, when I multiply by a same critical value, whatever that critical value might be, that's why this part of the equation gets smaller and our interval shrinks. Okay, so this is the math behind why that works. Cool?
What is the standard deviation we use for calculating a Z-score in the critical value?
So when we are calculating a critical value, we're not going to use a standard deviation. That's not true. I'm kidding. Just joking. Remember, Z-scores come from a standard normal distribution that has a mean of 0 and a standard deviation of 1. So the standard deviation that we're going to use to calculate that is going to be a 1.
Okay.
Yep. And we'll use that first thing tomorrow. We'll get nice and dirty with Z-stars. We love Z-star critical values. They're super easy, though, once you know how to do them. All right, cool. So there is our formula. P hat plus or minus Z star times the square root of P hat 1 minus P hat over N. Each part of this formula is very important and has a condition attached to it. So let's talk about those conditions now. Basically, it tells us why we use that part of the formula, okay? So here are the 3 conditions that must be met in order for our confidence interval to even be real, okay? So here's the formula again. P hat plus or minus.
Hi, Miss Linky.
Hi. P hat plus or minus the Z star critical value times the square root of p hat 1 minus p hat over n. So that's the formula for us to calculate and create a confidence interval. Each piece of this has a condition attached to it, and that's what we're going to go over now. All good. All right, so the first part that we're going to talk about is the p hat. This is the first part of the formula. This is our first condition. Condition number 1 is the random condition. The random condition. So, to ensure p hat is a good estimate of p, we must have an SRS from the population. P hat must be a good estimate of P, so we have to have an SRS from the population. What's an SRS? Simple random sample. Basically, guys, we got to make sure we take a random sample. We don't want no silly bias sample. That ain't going to work for us. Okay? That's our first condition. The next one has to do with the Z-star critical value. The only way that a Z-star critical value is going to be applicable in our problem is if I'm on a normal distribution. Z-stars only come from normal distributions. Z-scores only come from normal distributions. So, this is the normal condition. You guys actually already know how to check this one. In order to find out if your distribution is approximately normal for proportions, you just got to make sure the large count condition is good to go. All right? So, check the large count condition. Now, you guys know the large count condition, right?
Yes.
What is it?
And don't choose if we get larger and equal to 10, and then times 1 minus p also equal and larger than 10.
Oh no, you guys, we have a problem. How am I supposed to do n times p when I don't know p?
P hat.
Stick a hat on it, you guys. If you don't know the truth, just stick a hat on it. Okay? If you don't know the truth, just put a hat on it. So we're actually going to check the large count condition, but we're just going to use the hat, the p hat values. And the final one, guys, is the standard deviation. And to make sure that the standard deviation can be calculated, we have to check the 10% condition, which you guys already know how to check. We're going to make sure that 10 times the sample size is less than the population size. And now, after waiting for 2 months, I'm going to tell you guys why. Why is this condition even a thing? Here we go. This is the population. Why is it important that the sample size times 10 is less than that population size? Basically, what this is saying is that I don't want to take more than 10% of the population for my sample. I want to make sure that my sample is less than 10% of the population. And here's the reason. Think about McKinney. In McKinney, you have a different concentration of houses. The majority of the houses in McKinney are in Stonebridge Ranch area, this area around the school. People move to the Stonebridge Ranch area because they usually have similar, I'm not saying they're exactly the same, but they have similar values, thoughts, feelings about the world. They're going to maybe act in a similar way. You're going to have similar type people I'm, again, not saying that there's not an outlier here or there, but most of the people in the McKinney that live in Stonebridge Ranch are pretty similar in demographics and thoughts and things like that. Population of McKinney, east side of McKinney, less concentration of homes, more businesses, and the demographic on the east side of McKinney is different than Stonebridge Ranch, okay? So, when I start taking my sample of McKinney, okay? Start taking my sample of McKinney. I take a few people out of the population here. All right, I got my sample. There's a pretty good representation of my population. I got a little bit of everybody, right? If I start getting too big of a population, think about the fact that a larger majority of what's in this population comes from Stonebridge Ranch because there's a higher concentration of houses here. And so now I end up getting possibly a better chance of repeated opinions and values. What's that going to do to my estimate? It's going to bias it toward that higher concentration, okay? Yes, Aiden.
Why does that matter, though? Because if there's still a majority there, then the proportion's going to be the same regardless of how many you take.
Yes, so Aiden's question is, why does that matter? Because even if I'm taking less than 10%, I'm still probably going to get a proportion that's maybe disproportionate to the whole city of McKinney. Plus, if we have a large proportion that live in Stonebridge Ranch, then that is part of the population. That's the whole point of having this bigger population. So the reason that that's important, the reason that this is important is to make sure that each person's opinion is independent of other people's opinion in the sample itself. So this 10% condition ensures that we have independent samples.
So you're saying that just be like for example, if you're taking like a pool of like 1,000 people and you had like below the 10% condition or whatever, then the likelihood that they'd be more spread out is a lot higher than if you took more. So that way, like if you did take a lot more, they'd be like right next to each other.
Yes. Yes.
Because I thought you just meant like if the pool is like 60% like Stonebridge or whatever, doesn't matter how many people you take, it's still 60%.
Correct. You're absolutely right, but what you said is absolutely correct. So say it again.
So
Because he's totally got it, you guys. So listen to, actually, come here. Come here, Aiden. Come teach the class. Yeah, you do. Come here, I'll help you because I know what you said. Okay, you guys, Aiden hit the nail right on the head. He's going to teach class right now. All right, Aiden.
Hey,
Tell us.
Jimmy's, what's up?
Tell us what you said.
If you take less people from the sample, then there's a better likelihood they'll be more spread out and have different values than if they were like right next to each other.
Because when we start taking more and more in the sample, the probability that we get people that live right next door to each other gets higher because I'm increasing the people in the sample. So now I'm getting little pockets of bias, and that's not a good thing. Does that make sense? Good job, Aiden. Yes. Hello. Why the 10%? Yeah, so that's based on a so Catherine asked why the 10%? Why 10? Why not 20? Why not 42, right? So it is based on a binomial distribution when we look at the probability of having successes that are next to each other instead of spread out. So this ensures the selected ones in the sample are independent of each other. which reduces the chance of bias. This reduces our chance of bias. Guys, does that say it eliminates the chance of bias? Absolutely not. Could a sample that's only 5% of the population have too high of a concentration of one area? Yes, that can happen. But this reduces our chance of that happening. If I start getting too high of a sample size from the population, I'm going to start hitting pockets of non-independent selections. So I got to be careful there. These are our 3 conditions, you guys. These 3 conditions are not going to change for the rest of the year. They will be these 3 conditions. They will just have slight tweaks depending on what we're doing, whether it's proportions or means. We got to make sure we have a random condition. We got to make sure that our distribution is normal. And we got to make sure that we have independence in our sample by making sure the 10% condition is met. Cool? And if you have more questions about the 10% condition, ask Aiden. All right, cool.
It's cold.
Is it?
No, it feels great.
Okay. All right. So, here's what we're going to do, guys. We're just going to practice checking conditions now, okay? So check this out. Miss Lakey's second period class wants to construct interval for P, the true proportion of red cubes in this large tub, which includes over 3,000 cubes. This is true.
Told you.
That means it could be like 1 million because it said over 3,000.
But you know there's not a million cubes in here.
1 million.
Ocean says, well, that could be a million. There's not a million cubes in here, Ocean.
How much over 3,000 a million? How much over 3,000? Is it like 12?
I think I actually guessed 3,000.
All right. So,
Over.
here's what the class did. They take a sample of 251 cubes. 107 of them are red. Check if the conditions for constructing a confidence interval for P are met. First condition we're going to check is random. We want to make sure we got ourselves a random sample. This ensures that P hat is a good estimator of P. So, do we have a random sample?
Yes.
I mean, I know it just says sample, but guys, it was in my class. Of course I'm going to make them do it randomly. So we're going to just go with it. We got ourselves an SRS of 251 cubes. All right, next condition we're going to check. We're going to check the normal condition. We need to make sure that this distribution that's going to be created is approximately normal. That way we can get a Z-star critical value. So let's check. We're going to check the LCC. What's LCC stand for? Okay. Here we go, you guys. N times P has to be greater than or equal to 10. And N times 1 minus P has to be greater than or equal to 10. Oh no, you guys. There's a problem. I don't know P. We're going to put a hat on it. If you don't know the truth, put a hat on it. All right, you guys, I'm going to show you guys a cool math trick. I know your cool math games doesn't work, but I'm going to show you a cool math trick, okay? So here we go. N is the sample size, 251. P hat, that should be the proportion of red cubes in the bucket. Not the number of red cubes. Don't you dare put in a 107. But it is 107 over 251 because there is a proportion of red cubes of 107 over 251 that were selected. Does anyone know what 251 times 107 over 251 equals? Oh my gosh, you guys, look. It just reduces to 107. Isn't that a cool math trick?
Yeah.
Nice. All right, you guys. Now, check this out. 1 minus p hat. This is the proportion of failure. This is the proportion of failure. This is the proportion of not red cubes when we take that sample. So this is going to be 251 times 144 out of 251. Time out. Where did I get 144 from?
Subtracted.
Yeah, I took 251 and I subtracted the 107 red cubes. Now I have 144 non-red cubes. Hey, what's 251 times 144 over 251? Pretty sure it's 144. Do we have ourselves a normal distribution? Yes, we do, because this worked. Last one we're going to check is the 10% condition. This is to make sure we didn't get any pockets of bias when we took our sample of cubes. I don't want no bias cubes. All right, 10 times the sample size needs to be less than the population size. So 10 times 251. What's 10 times 251? Nice. Is that less than the population of cubes? Now, here's the deal. You don't know exactly how many are in the population. You may never know. But you do have a clue. The clue is that it's greater than 3,000. Is some number greater than 3,000 bigger than 2,510? Yes. All of these conditions work, you guys. That means you can now construct an interval that will estimate the number of red cubes or proportion of red cubes in the bucket. And we'll actually do that on Friday. Okay? So we'll come back to this problem on Friday. But the good thing is you've already checked the conditions. All right, let's talk about our good friend Barack Obama. Did you guys know, and I'm not making this up, Google it yourself if you want, did you guys know that Barack Obama is currently the most popular account on Twitter? He has 129 million followers as of last night at 11 o'clock when I looked it up. Barack Obama, Justin Bieber, and Katy Perry. That's the order. That's your order.
A lot of people followed them in 2012 and then never unfollowed them.
You think?
Well, yeah, because think about it. 2012, Obama's still president, Justin Bieber's releasing Baby, Katy Perry's
Right?
Fireworks.
Crazy. All right. But it is what it is. So, Miss Lakey wonders what proportion of Barack Obama's Twitter followers are male. So, she selects a random sample of 500 of Barack Obama's followers. In the sample, 308 of them are male. This seems different. Check to see if the conditions are met. First of all, do we have a random sample? Yep, we got ourselves an SRS of 500. When would it not be random? If it says that there was a non-random sample taken. Yeah, it would literally say not, yeah. I'll tell you, of the failed conditions, this one almost never fails. Yeah, they will fail, and we'll do one in a minute that fails, but this one almost never fails. All right, the next one is the normal condition. We got to make sure that this distribution is approximately normal, so we're going to check the large count condition. N times P has to be greater than or equal to 10. And N times 1 minus P has to be greater than or equal to 10. Anybody have a problem with this? Oh, I got to put a hat on it, you guys. Got to put a hat on it. All right. N, that's our sample size, 500. P hat, this is the proportion of males in the sample. That was 308 out of 500. What is 500 times 308 over 500? Cool math trick. It's 308. I know, right? This is greater or equal to 10. All right, cool. Next one, 500 times. All right, guys. If there was 308 males in the sample, then how many non-males or failures are there? 192. Our non-male friends are not happy right now. All right, you guys. We are left with 192, which is good to go. These two things work. Last condition, our 10% condition. 10 times the sample size has to be less than the population size. 10 times the sample size has to be less than the population size. 10 times 500, which is 5,000, has to be less than the population of Obama's followers. Do you think that 5,000 is less than 129 million?
Yes.
I think we're good, you guys. And now we can estimate, we can make an interval that would show the true proportion of followers that are male for Barack Obama. And we will actually do that on Friday. All right. This one. Jake wants to estimate the proportion of seniors at McKinney Boyd High School that like the cafeteria food because he certainly does not. He interviews an SRS of 75 of his 650 seniors and finds that 15 think that the cafeteria food is good. Check whether the conditions are met. Do we have a simple random sample?
Yes.
Yep. So random is good. We have ourselves an SRS of 75. In the interest of time, I will tell you guys that the normal condition will work as well. You're going to have 15 and 60, both of which are greater than 10. So I'll just tell you that that's true. 10% condition. 10 times n has to be less than the population. 10 times 75 has to be less than the population of MBHS seniors, which the problem told us is 650. Is this one true? This fails, you guys. So you might be asking yourself, Self, what happens when they fail? What do you guys think happens when it fails? I know you wish that the answer was you just quit the problem, but that's not the answer. You proceed with caution. And here's the deal. Make note of the failed condition with the final interval. Basically, guys, this is where the fine print comes through whenever you're looking at data on the news or in the newspaper or on Twitter or wherever you might be looking at your news. You indicate or report the interval, and there's a little asterisk, and it says see fine print. In the fine print, it says the conditions failed. However, here's the interval anyway, which is probably worthless. Isn't that fun? So there you go.